Am I audible and my screen is visible? Am I audible? Okay, fine. Thank you very much. So, good morning, everyone. Let us start today's session. Now, in the last class, we have seen how divide and conquer works, or the approach or strategy uh, used is in divide and conquer to solve a computational problem. Now, we have seen how divide and conquer is used in strategies used in binary search, in quick sort, in merge sort. And today we are going to see how divide and conquer strategy can be applied for sorting in elements in a completely a different kind of sorting technique known as quick sort. Now, the merge sort, if you remember in the last class what we have seen, divides the collection of elements or arrays into half, and subsequently into half till the problem becomes small, that is, till there is only one element left in the array, and it says that if one element is there, then obviously it's sorted. Now, in quick sort, what we are going to see is the problem is the same, that is, we need to sort the collection of elements in ascending order. Then the way quick sort works is it partitions the elements into two sets. Now, quick sort doesn't partition the elements into equal halves. It partitions the elements into two sets based on the pivot element. Now, in general sense, pivot is something, it's like a point which balances the right and the left. So, the set of elements, when it is divided or partitioned according to pivot element, all the elements to the left of the pivot will be smaller than the pivot element. And all the elements to the right of the pivot will be larger than the pivot element. So this is the basis on which the quick sort works. Now remember, pivot element can be any element, and it need not divide the array or collection of elements into half. So before we proceed further, let us look at what pivot is. Now let us consider this collection, these elements in a collection. It's stored in an array, obviously. Array, it starts from 1 and ends at 9. So there are 9 elements in this array. Now, let us consider this element 54. Now, is this element 54 a pivot element? Let us examine all the elements to the left of this pivot. Now, if you observe, we have element 28, 37, 45, and 15. All the elements to the left of the pivot are smaller than the pivot element. Now let us consider the elements towards the right of the pivot. The elements to the right, if you observe, we have 86, 92, 63, and 78. All the elements to the right are larger. Therefore, we say that this element 54 is the pivot element. Now, in this case, as an example, when we are considering this as an example, it's the middle element, but it need not be. Now, let us look at another scenario. Now, before we proceed further, when all the elements to the left are smaller than the pivot element and all the elements to the right are larger than the pivot element, that means the element, whatever pivot element it is, that element is in its sorted position. So the primary focus on what the quick sort works is on this the concept of the pivot or concept of the pivot element. Now let us look at another scenario. Now can we call this element 92 as the pivot element? Let us look at all the left side, the elements towards its left. All the elements are smaller. But what about the elements in the right side? Element 6, we have element 63 and 78. Both are smaller than 92. But elements on the right side should be greater than the pivot element. Even if a single element is smaller than the pivot element, we cannot call this element 92 as pivot. So therefore, element 92 in this collection is not a pivot element. Now what about this case, 63? Can we call this as a pivot element? All the elements to the left are smaller, so, and all the elements to the right are larger than the pivot. So therefore, we can say that the element 63 is a pivot element, and pivot element will be in its sorted position. What about this element 15? Though this is the first element, there are no elements to the left of pivot, but we have elements to the right of the pivot, and all the elements towards the right are larger than the element 15, that is the pivot element. So we can say that it is in sorted position. Now, if you observe, in this case, 15 was the smallest element. That is why there are no elements. Smallest element, and all the elements towards its right are larger. And then there is no element towards its left. So that means it should be the first element. And when it is the first element, obviously is the minimum element, and it will be in sorted position. The same is the case with the largest element. If you look at this, these elements, 92 we have, and there's no element on its right, and we have all the elements towards the left, and all are smaller. That means 92 is the largest element, and obviously the largest element will be at the end, or when it is sorted, it will be at the end or the last position. So we say that the pivot in this case is 92, and it is in its sorted position. Now, having seen about what the pivot element is, we will look at how the quick sort uses the divide and conquer approach. Remember one thing, quick sort doesn't divide the elements or partitions the array or set of elements into equal halves. It may not. It partitions depending upon the pivot element. Remember that. Now, the first phase is divide. There are n elements. They have to be partitioned. So that partitioning is based on the pivot element. Then the next phase is your conquer in the divide and conquer strategy. What conquer says here, or what conquers implies here, is that the two partitions has to be recursively sorted using quick sort. So once we find the pivot element and partitions the sets into left and the right arrays, subarrays, then the left array subarray has to be recursively sorted using quick sort. Even the right has to be recursively sorted using quick sort. And the third phase is nothing but once we get the solutions, we combine. Now here in quick sort, it's a trivial matter. Since the array, whatever the collection of elements we are sorting, the sorting is in place sort. That is, we are not using any temporary array to store the elements. We just try to swap the elements and their respective positions. So this is the three phases that are used. How divide and conquer strategy is applied using these three phases. Now let us look at the, how partitioning is performed. Now, in merge sort also, the actual algorithm for merge sort is only a couple of lines, and main computation is done in the merge algorithm. In the same way, even the quick sort algorithm itself is hardly 3, 4, 4, 5 lines of code. I mean, of algorithm. But actual computation or actual work is done in the partitioning process, and we call this process. I mean, we have a separate algorithm known as partitioning algorithm for performing this process of finding the pivot element and dividing the thereby dividing the array into two partitions. Now, so let us look at the how partitioning is done. Now consider this array where we have several elements, and obviously we have to sort these elements. Now we will take a variable v, and we say that we are initializing this as a pivot element. So first element is considered as the pivot element. It is initially considered as, it may not be a pivot element, it is considered as a pivot element. So we have a variable v, which we consider as a pivot element, that is the first element of the array. Then we will use a variable I, which will be pointing to the element, the first element at index 1, obviously. Then we will add an extra element at the end of the array. So its index will be 10. Though this is not part of the elements, we are adding an extra element. Now this is for convenience when we compare the elements. That is the reason we are adding. Then what should be the value? We say that there should be some large value which do not affect the values of the already present in the array. So we take this value and assume that value as a large value as infinity. So we have an extra element at the end of the array, and the value of that element is infinity. Next thing is we will take a variable as j, which will be pointing to the last element. Now, obviously, when we have added an element, that element becomes the last element. So j variable will be pointing to index 10. So remember that I variable points to index, the first index, or beginning of the array, or subarray also, and j index will point to the last element. Now, what we do is we move the I variable from left towards right, and the j variable will be moved from right towards left. Now, so at the first instance, we have moved I. I is pointing to element 2. We compare whether the element at index I is greater than the element at the pivot. Pivot is element 54. We have considered first element as the pivot. So 78 is greater than 54. So we stop. I will not move further towards right. I stops. Then we consider j. J moves towards left. Then we compare whether the element at index j is less than the element at the pivot, that is v. So element 37 is less than 54. So we stop. We don't move I and j. Now we swap the element at index I with the element at index j. Remember, pivot we are not. Pivot is right now there only to compare whether the element with at index I and element at index j. Now we swap the element at index I and index j. So these two elements are swapped. Then index I is moved towards left, sorry, towards right. Element 64 is compared with element 54. It is greater, so I stops. Then J moves towards left. Element 28 is compared with element 54. It is less, so J also stops. Then the element at index I is swapped with the element at index J. Then index I moves towards right. Element 92 is greater than element 54, so I stops. Element J, index J moves towards left. 15, element 15 at index J is smaller than 54, that is the pivot. It stops. J stops. Both the elements are swapped. Then index I move towards right. The element at index 5, that is 45, is it greater than element at 54? Element 54? No. So index I again moves. So remember that if the element at index I is greater than equal to element at V, that is the pivot element, then I will stop. If it is less than, then I will move, continue moving. Again, we check, that is the element 86 now at index I. Is it greater than 54? Yes, so we stop. We don't move I towards right. Now comes J. J is moved towards right, sorry, towards left. And J, element at J, 86. Is it less than 54? No. So J moves further towards left. Element at J, that is 45. Is it less than 54? Yes. It stops. So remember, I moves from left to right. And I stops if the element at index I is greater than the pivot. J moves from right to left. And J stops when the element at index J is less than the element at the pivot. At this stage, when I crosses J, we don't have to move I and J further. We actually found the place where the pivot element should be. So I is moved towards right and J is moved towards left until I crosses J. Until I index is greater than Jth index. When this is done, what we do is we swap the element at, that is the pivot element 54, the first element which we have selected as the pivot, with the element at J. So when we swap these two elements, 45 comes at first index and 54 comes at the index J. Now, if you observe the element at index J, that is 54, which we have selected as the first element, as the pivot element, will be at its position. So we start by selecting the first element, whatever element that may be, and then we try to shift the elements, the great larger elements towards the end of the array, smaller elements towards the start of the array, comparing with the pivot element which we have selected. Then finally, once the position of the pivot element is found, we place the pivot element at that index. Now, if you observe, all the elements towards its left are smaller than the pivot, that is 54. And all the elements towards its right are greater. Now, even the element, the last element, the infinity which we have added, even that is greater. So infinity element is just used as large value so that we start comparing. We move from left to right and all depending upon the elements present. So once we find the pivot position, the partition algorithm will return the index j. An element will be at its place. So what do we have to do now? Now what do we have to do? We have to sort the left partition and we have to sort the right partition. Left partition, all the elements are smaller than the pivot. So pivot element is at its place. All the elements towards the right are larger. So that becomes the right partition, and we have to recursively again apply the quick sort and perform the sorting of these partitions. So this is how partition algorithm will work. Now let us look at the partition algorithm. It's called as the partition. It takes three parameters. First is the array A, and the next parameter is M, and the third parameter is P. Now we'll come to know what this M is. M will be pointing to the first element of the array, that is the index. P will be pointing to the last element. Now what is the last element? It is not 9. So when the partition is initially called, it will, if there are n number of elements, then P will be passed as n plus 1. P will be passed as n plus 1, and that element will be having a large value. So a partition element uses three parameters, that is the array A, that is the first parameter, M, which is the first index, P, which is the last index of the array, or whatever sub-array we are trying to partition, whether it is left or right partition. Then we use V as a variable and assigns A of M, which is nothing but the first element. We are selecting V as the pivot element. Then we have index I and index j, which points to M and P respectively. Then we will use a repeat until loop, just like a do-while loop. This is do-while loop, repeat until loop. We perform this repeat until loop. That is what we have to perform is we have to move I towards right and j towards left. That is what we have seen just now. This has to be done until I becomes greater than equal to j. So when I crosses j, this movement of I and j towards left and right should stop. So within this do while loop or repeat until loop, we have another repeat until loop which will move I to I plus 1 until A of I is greater than V. Once A of I is greater than, that is the element at index I is greater than the element at the pivot element, then I stops. Then we have to move j towards left. So we will decrement j. We will decrement j. So j we use, and again j has to move to till the moves towards left. So j will be decremented. So j variant index will be, we will be using j equal to j minus 1, and this is done until A of j is less than the pivot element. That is what we have seen the condition there. So we move j until A of j is greater than less than equal to V. Now once these two things are done, once we find once I and j stops, then if I is less than j, then we will interchange. Interchange is nothing but swiping the element at index in the array A at index I and index j. So we swap, and, and once I crosses j, that is I becomes greater than j, we found the position of the pivot element. So this two repeat statements will move I and j subsequently till I crosses j. This is what the working we have seen just now. And once I crosses j, the repeat until loop or do while loop in programming language stops. And then what do we have to do? We have to swap the element present at index, that is the pivot element index m, with the element present at index j. So we use a of m equal to a of j and a of j equal to v. So this part, these two statements is going to swap the element and pivot's position is found. And finally, we return the index of the pivot. Remember, we return the partition algorithm partitions the elements and then returns the index of the pivot element. It doesn't return the pivot element. Pivot element is at its sorted position place. It returns the index of the pivot element. So this is how partition algorithm works. Now, before we look at the quicksort itself, let us try to analyze this partition algorithm. We have a repeat until, that is, we have two repeat untils, and these is going to work for n number of times. Now, these repeat until statements are within an outer repeat until loop. So this is like a nested loops. And the statement if I less than j, that is to check whether I crosses j or not. This is primitive statement. And even the statement which is there to swap the pivot element with the element at index j, these are also primitive statements. So we are bothered actually about n and n times with these two repeat statement works. Now remember I said earlier, and there are two loops, nested loops, then the time complexity is quadratic. Now that is when the first loop is executing for n number of times. And the second loop, the nested loop inside that also runs for n number of times. Then it will be n square. But here, the outer repeat loop will not run for n number of times. It runs only until I is greater than j, until I crosses j. So it will not run for n number of times. On an average, it will run for half. So that is why we say that. And every time it is not that it's only half. It's maybe it depends upon how the elements has to be partitioned. So it will never run for n number of times. And the other statements are primitive. So therefore, we say that the partition algorithm takes O of n as time complexity. Now, before we move further, one more clarification. Now here we have selected the first element as partition. First element as partition element to perform partition. Now it does not need not be. You can select the last element also as the pivot element, but your procedure of how you write the partition algorithm will differ. So, in what we do is, for the sake of flexibility and convenience, we select the first element as the partition, as the pivot element for performing the partition, and then proceed with the steps which we are seeing. And then let us come to the actual part. Now, let us look at the quicksort, the pseudocode for this quicksort algorithm. The first parameter which is passed for this quicksort algorithm is the index p, which will be the first element, and the second parameter as the index q. Now Q is sparse. Obviously, if there are n number of elements, Q will be n initial. Then we check if P is less than Q. If this is true, that means there are elements which needs to be sorted. There are certain elements which have to be partitioned. So if this is true, then we perform partitioning, passing array A, P as the first index of the first element. And here you can find that Q was the index of the last element. But since we assume and we add an element at the end, we pass the index as Q plus 1. That is, if there are n number of elements, we pass the index as n plus 1. Now, once partition algorithm completes, it returns the index of the pivot element. So when the index of the pivot element is returned, that element is it in its sorted position. Then we have to perform the quick sort on the left partition. So left partition will be from index P till j minus 1. Partition, this element j is sorted, but is already sorted. It is in sorted place. So we recursively call quick sort on the left partition, passing P as the first argument and j minus 1 as the second argument. Then we will recursively sort the right partition. So for the right partition, we will call quick sort and pass j plus 1. Remember, j element is the partitioning element. It's a pivot. It's already sorted. So we have to sort the remaining element, that is from j plus 1 index, that is the left index, to q. Now it's not q plus 1 because once it is called, again it checks, and here partition is done by passing q plus 1. So don't bother, we just pass q over here. So this is how quick sort works. Now remember, in merge sort, we perform recursively called merge sort, then we perform merge or merging of two sorted arrays. In quick sort, we first perform the partitioning and then recursively call the quick sort on the left partition and the right partition. Remember, that's the only, that is the way it works. So if there is a question asked about what is the difference between quick sort and merge sort, you have to explain about how merging is, the difference between merging and partitioning. And merge sort actually does the work after performing recursive steps, recursive calls. Quick sort does the actual work before performing the recursive calls. So that is the difference. Now let us try to analyze the quick sort. Now if you see quick sort, let us assume that obviously this is a recursive algorithm, so we have to consider the recurrence relation. Now if you consider quick sort, takes t of n time as t of n as the time, then partitioning algorithm we have seen it takes n, it runs for n number of times, so it's going to take O of n or n times. Then quick sort is recursively called on left partition and right partition. We are assuming, though left and right partitions may not be in equal size, but we assume, we consider that on an average case, the partitioning element is always going to be in the middle. So we assume and we say that partitioning is divided by 2. The left partition is half of the elements, right partition is half of the elements. So what happens is the total, if we add up these things, we will have 2t n by 2 plus n. N is this, plus n is nothing but O of n for partition, plus n. And this is the recurrence relation when n is greater than 1. If there is only one element, again, there is nothing to sort there. That element becomes, there is nothing to partition actually. and that element becomes the partitioning element, pivot element itself. So we say that it takes a unit of time if n equal to 1, and if n is greater than 1, it takes 2t n by 2 plus n. Now, if we solve this recurrence relation, we will get the answer as O of n log n. Now, remember that this O of n log n is, let us look at this O of n log n. Is it in terms of average case or best case or worst case performance? Now here, let us take and assume that there are n number of elements, and T of n is the time taken. On an average, for the quick sort algorithm, let us construct a tree, or even here we will try to construct a tree as we have seen in the merge sort. Now, at this place, there are n number of elements that has to be partitioned, or quick sort has to be performed. On the second level, quick sort has to be performed by n by 2 and n by 2. Two separate recursive calls are made, but number of elements will be n itself. Then on the next level, next recursive call, n by 4, n by 4. This is on an average, we are saying that this partitioning elements divides into half. Even at this stage, it will be n. So if you see, we have number of n's. How many times? How many levels we have? Till this t of n by becomes trivial. So when will it become trivial? When the tree, when at the leaf node, it becomes trivial. That is, only one element is there, and it isn't. That's the pivot element. So it's actually the height of the tree which we are bothered about. That is, recursion will run for height of the tree. And height of the tree is nothing but if there are n number of elements and each are divided into two, it's like like a binary tree, left half and or left partition and right partition, or left child and right child. Then the height of the tree will be O of height of the tree will be log n if there are n number of nodes. And then we are calling this n number of times. So this will be n log n. Now this is the time complexity is O of n log n, where in the best case and in the average case. The best case is when the elements are random stage. Average case is when we consider that the partitioning element is always going to be in the middle element. Then what about worst case? Now worst case is when the elements are already sorted. That is, when the elements are already sorted and we are trying to perform quick sort. That is the worst case. So if the elements are already sorted and you try to perform quick sort, the time complexity will be worst. Let us look at how it happens. We have T of n as the time taken for this quick sort. Now, at this place, it will be n number of elements. When we sort, and when the elements are already sorted, we are selecting first element as the pivot element. Will the position of that element change? No, it will not change. And the pivot element remains at its position. We are left, there will not be any elements towards the left because that was the element which is selected and that isn't already sorted, and it will be in its place. So we will have n minus 1 elements to the right in the right partition. There will not be anything on the left partition. N minus 1 elements on the right partition. Then when again quick sort is performed on n minus 1 elements, we will have n minus 2 elements because that element pivot will be same and it will not change. Now this goes on till we have kth elements in the last iteration, recursive call, where we have only one element. Now, this is not a balanced tree. If you see, this tree only has right child, and it is known as right skewed tree. All right child, right child. So its height will not be log n. Its height increases, even though there are n number of elements, the same number of elements. But since the elements are sorted, the recursive nature of the calls or the tree which is created is recursive nature will, when we call a quick sort algorithm, there will not be any left partitions, only right partitions will be there. And every time the right recursive call is made on the right partition, only one element will be less at each stage, at each level. So if you sum up these, the height of this tree will be n into n plus 1 by 2. This is summation of n actually, which is n into n plus 1 by 2. So in worst case, the quick sort, the time complexity of quick sort is O of n square. And remember, worst case is when all the elements are in sorted order. That's the worst case. So this was all about quick sort and how partition is done and how quick sort is performed. So these were some of the algorithms or problems that can be solved using divide and conquer approach. Now let us look at another problem. This is a geometric problem known as closest pair. Now till now what we were seeing the sorting problem or we were seeing the switching problem. But this is a geometric problem known as closest pairs. Now here this comes in the category of brute force. So we will look at what is the problem with brute force and how can we rectify it using divide and conquer. Now assume that we have an x and y plane, or I mean a two-dimensional plane of x and y coordinates, and we have several points. Now the problem is, or what we need to solve, we need to find who is nearest to whom. That pair we have to find. Which pair? Which point is nearest to which other point? That is closest pair. That is what we call. So what we do is we will divide. Let us first look at brute force approach. What will be the brute force approach? Brute force approach means without thinking optimally, efficiently, we try to find the solution to the problem. So here, this is geometric, what do we say, points. Every point has its x and y coordinates. So finding the distance between the 2 points is nothing but we use Euclidean formula, that is x2 minus x1 whole square plus y2 minus y1 whole square divided by 2. And whole root of that. So that gives us the distance between 2 points. So what would be the exhaustive or brute force approach? Brute force approach would be to take 1 point, find its distance to all other points. So if there are n number of points, you take 1 point, find the distance to all other points, n points. That runs for n times. Then take another point, find its distance to all other points n times. So if there are n number of points, and you find with each iteration, take a point and find with n number of the distance with n number, then the time complexity of the brute force approach would be n square. That is the brute force way of computing the closest pair. And obviously, O of n square is not that efficient. So, is there any better way? We use divide and conquer approach for closest pair. What divide and conquer approach says that, and it gives us better time complexity. What divide and conquer approach says that divide the elements into 2 partitions. And this is not based upon half. It is based upon how many elements are in left side and how many elements are, how many points are to the right. So once we divide it, we have a partition as A, and let's call it as left partition with all the points on the left side. And the blue dotted line is the, what do we say, is the x-axis, the value of x, which divides these points. So we are not dividing the points based on value of y. We are dividing based on x coordinate. And let us have the next partition as B, two partitions A and B. B, all green dots comes into partition B. So this is the divide approach, divide and conquer approach. Then what we say is find, or recursively find, the smallest distance between the pairs, closest pair, in partition A, partition B. So again, for partition A we can divide, partition B again we can divide, till there are only two elements. So when there are only two elements or 2 points, that means the solution is small, and we can directly compute the Euclidean distance. So instead of taking all n number of points and trying to find distance between each point, we divide it only till we have left with only 2 points, and we can easily find the distance between them. Or there's no loops or iterations involved. Now assume that partition A, point B and H is the minimum distance. Let's call it the AD. So recursively assume that we found, we again recursively applied this closest pair part, divided this array A, partition A into again half, again half, again half. Assume that we found the minimum distance between among all the points in A, that is the red dots, as D of A. And then with B, respect to B, the partition B, assume that we divided and we found the smallest distance between the pair J and F. Let's call it that D of B. Then we combine. Now we try to find who is minimum between the pair in A partition and pair in B partition. So minimum of, we select D. D is nothing but delta, or sometimes it's called as D. D, the distance between minimum of distance of A and distance of B. That is the elements from partition A and elements from partition B. In this case, let's consider D of B is minimum. Then this D, whatever is the distance, minimum distance we found, from the partition line on x-axis, we will have another line drawn with a distance of D, even to the right side, even to the left side. So blue dotted line is the dividing line. We create 2 more imaginary lines. Less D distance and greater D distance, the delta distance. Now, all the other points which are towards the left or towards the right of these two has to be ignored. And we consider only this region between the 2 yellow lines, which are D apart from the midline. Why? Because there is no need to consider other things. They are definitely, if you join the points from this region to any other region, obviously it will be greater than D distance. And we don't want this. We found the minimum till now is the D distance itself. So what we do is, we only have these many points now. So actually, when we divide a line, we have 3 cases. The smallest, closest pair can be in partition A, or closest pair can be in partition B. So these are the 2 cases. The third case is that the closest pair, one point of the closest pair can be in partition A, and the other point of the closest pair can be in partition B. Using dividing approach, we have found what is the closest pair between in A, what is in B. Now we are trying to find If there exists a closest pair whose one point is in region A and the other point is in region B or partition B. So now we have only left with these points. So we select point horizontally, vertically, y-axis, we select a point, the highest point, and then we compare this box, blue box which you see, we try to find whether a point lies between these two boxes. What is this box? The width is d itself because that's the blue line. What is the height? From D, vertically distance of D, and vertically to the top and vertically towards bottom. So we get this region as the rectangle. Now we only, at the most, what we have to compare is 6 extreme points. Those are the 6 extreme points we have to compare. These 6 extreme points. Now, none of the points here will lie within the shaded region of A side. If it lies, that means what D and DB, what we computed, is wrong. So we don't have to compare the points among the ones which lie in the shaded A region. We only have to compare points which lie towards the shaded B region, and which will be at most 6 points. At most 6 we have to compare. Now in D, does any point lie within this region? No. Then we select the next point in region A, within the shaded region, that is the red one. Are there any points which lies within this region of the blue two boxes? No. So that means we have not yet find anything closest than DB, that is J and F. Then we have a last point I. When we draw the region of the 6 point from I, point L lies within that region. So we found the closest pair which is closer than J and F, that is the distance dB, closer than the distance dB. So this is how the closest pair algorithm works. So the brute force approach is to take one point and compute the distance with all the other points. So that runs for n times, and for n points we have n square as the time complexity. And the other approach is divide and conquer approach, where we divide the region into 2 halves and perform the divide and conquer strategy as we have seen now. So this was all about closest pair. Now in the next class, we will continue with the other topics. If you have any questions as such, please let me know, or else we will meet in the next class. If you have any questions, just let me know. Otherwise, you can log off and we can meet in the next class. That is on Tuesday, I suppose. Please log off. If there are no questions, please log off and join the other class. What is the syllabus for first intern? Very good. We will consult with the